Good morning. I'll be right back. I have to use the restroom. Been drinking a lot of tea this morning. Hello, Eric. Good to see you. Hi, Sarah. Sarah, I know we just ended a relatively long discussion about philosophy, so I don't think we're gonna start for another 3 minutes. You too, Yona. If you guys want to take a little breather for 3 minutes, I highly welcome you to do so. All right, just chill out for a second. You're here, Eric. Day 36 of quarantine. Good morning, Becky. Good morning, Almar. So good to see you. We're going to start at 10:21, all right? I want to give everyone a chance to kind of, you know, get with it, as they say, all right? Good morning, Chris. Oh, Grandmaster. Grandmaster Chris. I'm sorry. Yikes. Oof. One more minute. No likes. Yeah. Can I like my own video? I can't. That would be kind of sad, right? I do have a second. I could watch this from my phone, and then maybe I could like it. Good morning, Attune. All right, it's 10:21. We're starting the stream later than usual, and we only have 8 people out of 34. This is a little sad. I'm also noticing for this particular assignment, we are a little below usual. All right. I still have 23 turned in, and 11 people who have not turned it in. All right. I'm not going to call you out. You know who you are. Well, I don't think any of you are really in the chat. But if you're watching, a little delayed, you know who you are. Okay. All right, so let's get started, right? The big idea of the thing I wanted to let you see for yourself in the FET simulation, I mean, in addition to kind of like playing around with it, because there are some pretty fun circuits you can make, the first thing is to see that when I go to a hardware store and I see like a 60-watt bulb, it's not going to output 60 watts all the time. It's going to depend on how it's placed in the circuit, right? So for example, like if I look at bulb A and bulb B in the series circuit, if bulb A is brighter in series, it has more power than bulb B in the series circuit. But when I place them in parallel, bulb A is now dimmer. So bulb A's power decreased. So its power wasn't constant. Yet the way the hardware stores or like light bulb manufacturers like label bulbs would make you think that it's constant. What power isn't constant because it depends on the voltage and the voltage drop across the element and the current running through that element. And we know that that can change based on any type of circuit, right? Even with between two series circuits, right? If I kept the same series one, right, and I have my 50 ohm bulb and my 100 ohm bulb, were those the numbers? Let me see. Hold up. Let's see. Why can't I see it? This is very strange. No, not that one. Sorry for the delay. It's a little awkward. Yeah, I have a 50 ohm bulb and a 100 ohm bulb, right? Good morning, Ayanava. You missed the lecture on Parmenides. You naughty boy. So we have a 50 ohm bulb and a 100 ohm bulb, and I attach it to a 60 volt battery, right? According to our mini lab, right? Instead of now constructing a circuit with the same set of materials, good morning, Caitlin, in a parallel configuration, what if I kept it in the series configuration, but I just doubled the voltage of the battery? So I went from 60 to 120. So here, even though I don't change the configuration, which is like the series configuration, and in this setup, I'm still gonna have that the 100 ohm bulb is brighter. It has a higher power output. But what I'll find is both the power outputs of both bulbs will increase, right? Because if once I increase the voltage of the battery, the overall current in the circuit increases and the voltage drop across each resistor will increase, which would mean P is IV, it'll increase, right? So your power output for the bulb does not only depend on the type of circuits it's in, but just the values of the stuff in the circuit in particular. If I change the battery, I'll change my power. If I change the series to parallel, I'll change my power. So all this goes to say is that power is not constant within a bulb. What is the only thing about a bulb that remains constant? Kind of like What's the only thing about this cup that'll be constant? Is it its net force acting on it? Is it its temperature? Is it its mass? It's the mass, right? No matter what I do to this cup, the mass will always be constant, okay? What about a light bulb is always constant, besides its mass? No matter where I put it in a circuit, what type of circuit, exactly, right? So resistance is the internal constant property in any element, all right? So if resistance is the thing that's constant, why the heck are my power companies and my light bulb manufacturers writing out the wattage when the wattage changes? Why don't they just tell me the resistance of the bulb? I don't know. That's a really great question because not everyone takes AP Physics 1 and are capable of doing the very basic calculation. So then what does the power output refer to? Does resistance not change as the material wears down or anything? Generally not. To answer your question, let's move to the board. Okay. And let me get a marker. What the heck? Where's my marker? Oh, there it is. Oh. Okay, so I gotta put my laptop on this so you can see the top part of the thing. Okay, nice. Okay, so let's go over like the basic stuff. All right. If power equals current times voltage, what's one way, right? And I know that power is consistent everywhere in my house. Every outlet. Okay? Every outlet in my house, the bulb is going to be the same brightness. Assuming I don't have one of those dimmer switches, we're not going to talk about how this works. All right? So if that's true, and the I and the V are the same, what does it say about how the circuits are constructed in my house? My house circuits look like this or like this. What is the way I can guarantee I and V are the same each time I put in a bulb? Like if I have bulb 1 here, already plugged in, right? And I add a second bulb. And I have bulb 1 here, and I add a second bulb. Which circuit makes sure that the power output of 1 does not change when I put in a second bulb? That the current and the voltage drop across that bulb is going to be the same when I add a second bulb in. Sarah says series. Chris says parallel. I'm going to open the forum to other students. Series. Let me rephrase the question. Whenever I add an additional bulb, I want the power in the first bulb to be the same as if the other bulb wasn't there. I don't necessarily need the two bulbs to have the same current. I need I1 initial to equal I1 final. I need V1 initial to equal V1 final. What I don't need is I1 equal to I2. This is not important. This is not important. Why is that not important? Why is this important? Because I want power of the first bulb to equal power of the second bulb at, power of the first bulb at a later time, right? Because I want my 60-watt bulb to always act like a 60-watt bulb. I don't need, right, P1 to equal P2. Who says that? If I have a 60-watt bulb and a 40-watt bulb, I want both of them. I want the 60-watt bulb to act like a 60-watt bulb, and I want a 40-watt bulb to act like the 40-watt bulb. It's parallel then, right? Because as soon as I add the second one here, the current decreases, which then decreases the power output of the first bulb, right? This is extremely problematic. What this says is every bulb that I add means all the bulbs in my house get dimmer, right? That's no good, right? So what this really says is everything is always going to be my parallel circuit. And this is exactly how your house circuit board looks like, right? Yeah. And the beauty of this is I don't care how many things I have unplugged, current will still run. Here, if you'll notice, the other reason why it's impossible for your house to be laid out this way is if this circuit only runs if all four things are plugged in. Because if there's nothing here, the current's broken and it's the same thing as an open switch, right? So it has to be this way. And the other really cool conclusion you can draw from that, or the reason why that's true, is because no matter what I do here, the voltage is the same in there. And if the voltage there is the same, then the current's the same because the resistance is constant, right? Okay, so now we've kind of gone over what the circuits in our house look like. And now that we know that's what the circuits look like, we can talk about the power output that's labeled on every one of our appliances. But to do so, I want to go over an alternative formulation of the power formula. All right, if I have power equals I current times your voltage drop, okay? Well, guess what? I also know the voltage drop is equal to my current times my resistance. So I want to express my power in terms of internal qualities. So what do you think I'm going to do? P equals I squared times R. Does everyone see how I got there? Combining this equation and then this equation, I get this one. All I do is substitute V equals IR for that V. So this is I times R, and that becomes I squared R. The other thing you can do is to say that I equals V over R, right? I divide both sides by R here. And then I can write P. If I plug in V over R for this I get V squared over R. All right. these are our three equations for power, okay? But I'll never tell you to memorize any one of them, all right? All you have to do is memorize these two. Ohm's law should be a given at this point. P is IV. I like IV because there's no squares and stuff. So you never have to remember like, oh, which one's squared? And then from there and there, you can create the other two, okay? So when I have a 60-watt bulb, what does that mean? A 60-watt bulb. I want to talk about what's inside that bulb. That 60-watt bulb is not always going to have a power output of 60 watts. What I'm curious about is, what's the resistance of that 60-watt bulb? That 60-watt bulb. Anytime you see wattage, it needs to go in quotes. All right. So what is the resistance of this 60-watt bulb? Well, in America, this voltage that is everywhere in your house, the voltage drop across every outlet that's plugged in, okay, is 120. It's 120 volts. What does an extension cord do? It just adds, if I plug in an extension cord, it just does this. It adds more things in parallel, right? Does that mean I can just add more and more extensions and have a bunch of parallel stuff here? Yeah, but guess what that does to your total current? It's going to make your total current huge, right? Because eventually all of these currents have to add and combine and like pass through this one voltage source. And if that current's too big, the fuse in your house will break as a precaution because your wire will go on fire. It's too hot if there's too much current. Okay, so this 60-watt rating is assuming it's plugged into a 120 voltage source in America. So as a very quick example, an American 60-watt bulb, right? So USA, yeah, not a lot to be proud of in this country right now, but you know, America. So an American 60-watt bulb, what's its resistance? Let's use this formula to calculate that out. Everyone should be doing this. Everyone should be doing this, okay? You have to assume that the V is 120 volts because we're in America. When you have the answer, please put it in the chat. In the meantime, I'm going to brew my fourth pot of tea. What, he's making us do calculations like real class? You betcha. It's 240 ohms, right? Wow, you guys all did it at the same time. That's incredible. All 5 of you, right? Yeah, so an American 60-watt bulb has a resistance of around 240 ohms. And that's a misnomer because that means it has 200. So an American 60-watt bulb is actually just a tungsten resistor that has a resistance of 240 ohms when it's around 5,000 degrees Kelvin. So around room temperature, that tungsten filament probably has a resistance around like 100, right? And as it heats up, its resistance increases. And when it reaches its operating temperature, it'll be 240 ohms. Dumont, you're a day late, okay? So with regards to all of this, right, let's compare this to another country. Japan. No, not Japan. The UK, right? Our English overlords. In England, the standard voltage supplied by an outlet, if you guys didn't know, right? The voltage in England is 230 volts, which is much bigger than the American, you know, 120 volts. Why is this crooked? This is really making me upset. Oh, that fixed it. Okay. So a 60, what would an English 60 watt bulb be? Right, well, let me do this calculation. So 60 equals 230 squared over R. So R is 230 squared over 60. Yikes. This is 23 times 230 over 60. Yikes, 6. This is 23 times 115 over 3. Yikes. Crapola. Let's multiply that out. Yeah, okay, 23, 115. Let's watch your teacher do some math. Cool. And then I need to divide this by 3. All right, cool. Right, so the resistance of an English 60 watt bulb is 861.66 ohms, right? Oh, thank you so much. Okay, right, so different bulbs with their wattages, so that's why we always call it wattage, because it's assuming it's going to operate at a certain voltage. And then you can ask yourself, well, why are we able to assume things are always going to operate at the voltage that they were designed for? Because all of our circuits are parallel. Like all of our outlets are part of a parallel circuit that will always supply the same voltage to the outlet. And that's why we're able to just say, oh, 60 watts, 50 watts, 100 watts, because we can always assume it's always, in our country, at least always going to be 120 volts. In the UK, they can always assume it's 230 volts, blah, 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 blah. Should they just label the resistance? If I go to a hardware store, yeah, I would prefer the bulb be labeled 240 ohms. What's so hard about that? Why does it have to be labeled 60 watts for the simpletons, right? No. It'd be much easier. And you know why? There's another really important thing why we should always label it with the resistance, because even though everything is designed to operate at 120 volts, in reality, if you took a voltmeter, don't do this though. It's not safe. It's only safe for a certain configuration of a circuit. So I wouldn't recommend just taking a voltmeter to your thingy thing, okay, to your outlet. You might shock yourself. We frequently get readings around 110 to 115 volts around our outlets because like our power supply isn't like super perfect, okay? So because of that, a 60 watt bulb only really performs like a 55 watt bulb or a 50 watt bulb if it's undervolted, like if it's operating at 110 volts instead of 120. And that happens a lot because our power grid's like not super perfect. So shouldn't we just label stuff by resistance? Yes. Why don't we? I don't know. So this is power in a nutshell. I'm going to give a pretty easy worksheet that just goes over this. If you can do the thing due today and understand the worksheet that I give today, you should be okay. All right. It goes more into like the power stuff and like what it means. I don't know what you guys are talking about in the chat. I mean, the answer is clearly 881.66666. I mean, we got the same thing, so I don't know. This is not physics, but why do different countries have different voltages? Because when different countries were making their power grids, Yona, they weren't communicating with each other. So the numbers are actually really random. Like 120 isn't special at all. It just was the number that we kind of came up with. And 230 is not special. Japan, I think, is a little special. It's 100. I think they really wanted 100 volts. It's kind of like neat. But yeah, no one really communicated with each other when we're doing this. So we all came up with random numbers. Now, that's like the first batch of countries, and then like when you have other countries that develop an electric grid after the US and the UK and stuff like that, then they started copying one of those countries because it's nice to be able to use the same appliance no matter where you go. This is why you can't use Japanese things here, you can't use British things here, and vice versa. Like a common safety measure that we've done to make sure that that doesn't happen is like all of those countries have different shaped power plugs. So you'll never make the mistake of actually plugging it in the wrong thing. There's nothing specific about the shape of a power plug that makes it better, or like, well, why is Britain's power plug different than ours? Why is Japan's power plug different than ours? Like, that actually is because the voltages are different. Like, we've done that so people don't accidentally plug in appliances from one country to another one. Because if that happens, it's a completely different wattage. If I plug in a 60-watt bulb, an American 60-watt bulb, into a European British circuit, then that 60-watt American bulb is going to be around like 1,000 watts in Britain. And it'll get really bright, really hot. It's going to get a lot hotter than it was designed to do, and it'll probably fail, and it'll burn. Yeah. Why does America use the imperial system? You mean, what's the customary system? Oh, that's a real thing. I have no idea. Ah. Customary units, Yona, there's an interesting history behind it. A large part of it was because we're a British colony, and the customary system is derived from a lot of traditional British units. It's just the legacy of English colonialism. And after we declared our independence, a lot of former British colonies went over to the metric system, and it's like, yeah, screw Britain, but we just didn't. I know. Okay, that's it. Look for the PDF I'm gonna send today. It's due tomorrow. This is a pretty fast-paced week in terms of work, but I think conceptually it's kind of light, right? So there's like the balance. We are going to be going, at a lighter pace than if we were at school, and I'm really trying to avoid overloading you, like on your return from spring break. But yeah, I would have hoped to finish circuits, and that includes power before spring break, but we couldn't. So this is the last week. Tomorrow will be the last lesson on circuits. All right. So get pumped about that, and I will see you tomorrow. All right. Look for your next assignment. It's due tomorrow morning. Love you guys. Have a great day.